transfer interaction. So all the organizers probabilities together. When I see something to this presentation, you might have to like it's a lot of effort. So this kind of from this. Okay, so today I'm going to talk about AI for mathematical and algorithmic stories, something I've been doing for the last couple of years. And I will try to give a very brief introduction and then start talking about some pieces of work I've been involving. I will not go into the details, just what we have, what's going on, and what kind of result we can get in each. And we'll go through how to answer, concept, and overall. Some of these are very recent works, so I hope you enjoy it, learn about it. And then, so yeah, I will kind of start kind of the presentation a little bit through the particular problem of matrix multiplication, that's the algorithm for multiplying matrices. First, because kind of it's the first thing that I can do with the tester, but also because, well, we have a lot of these algorithms, it kind of although you present everyone. And it's easy to see the transition when we go from one method to another. Okay, so let's get started. As I had the goal of this presentation, the goal of our team is to discover new knowledge and efficient algorithms for impacting problems using AI. That's as I can do the high level, but it's still like North Star that we try to deploy. And as I said, like we unfold this presentation in the context of logic multiplication, so let's jump straight into it. How do we multiply matrices? Let's take the simplest example. We have two vertical matrices, and how do we multiply them together? Well, we all learned this in high school. This is the algorithm. Okay, so I just rewrote this a little bit differently, as usual, just to clearly separate multiplications from additions. But this is the algorithm that you can follow to compute the output matrix C. And well, you can see that this algorithm involves 8 multiplications, and in the 1960s, Strassen was trying to prove that you can do better than 8, and by accident, he showed that you can actually do better than 8. And this is the Strassen algorithm, and with a breakthrough back then, and still one of the kind of seeing the beginnings of all this work. And there's ability to combine the coefficients of the input matrices is as a way to reduce the multiplications by 1. So why do we care? So essentially we go from 8 stellar multiplications to 7. So why do we care about that? That might not seem a lot. Like again, we go from 8 stellar multiplications to 7. So what? The thing is that if you consider bigger matrices, M, you can split them in blocks, and then the algorithms from the previous slide still apply here. And the only difference is that everything is in capital letter. So it was scalar before, now it's matrix. And then, so we go from 8 matrix multiplications to 7 matrix multiplication, and that starts to be a big difference now. And the thing is that for these matrix multiplications, these 7 matrix multiplications here, each of the operations is itself a matrix multiplication. So you can recursively apply Strassen for each of these 7 matrix multiplications. So it's like splitting n by last and so on. And that would give you in the end that you would reduce the complexity of matrix multiplication from NQ to N2 is 2.81. And that was the breakthrough. Like you can do better than NQ. And of course, once you're there, you might think, okay, we got to this 2.81 using 2x2 based blocks, 2 by 2 matrix multiplication. Well, it can be shown that you can do better than 7 multiplications. So 7 is the best you can do. But of course, natural question: what if our base matrix is 3 by 3, and we split in 9 blocks each matrix, or 4 by 4, and so on, right? And if these are small matrices, so surely we must know what's the best way to multiply them. Well, turns out these are still open problems as of today. So the only early case where we know how to optimally multiply matrices in terms of number of multiplications is 2 by 2. And the reason, well, is well, the number of multiplications, this is the state of the art, 23 and 48, that leads to this complexity when we apply it recursively. But the reason is it is hard to find efficient matrices. And that's why we think that AI can help us here. In fact, this 48 here was discovered by so it's a little bit different. Okay, So with that in mind, let's jump into AlphaTensor. And first of all, I just want to show some of the kind of results and we get with this. I mean, there are many numbers in this table, but essentially, yeah, just to focus on one particular one. Here we have slices of matrices, okay? So 4 by 5, 4, 5, 5 means multiply a 4 by 5 matrix times a 5 by 5 matrix. So how many multiplications do you need? Well, before AlphaTensor was 80, after it was 26. That's what this table is saying. And you can see there are a few instances in which we improve state of the art with AlphaTensor. So how do these algorithms look like? Remember I showed stressing a few slides back. So how does this look like in the case of this particular one, 4 by 5 times 5 by 5? Well, here's the full algorithm found by AlphaTensor. Well, it's a little bit, doesn't fit on the slide, but I promise it has 76 multiplications. Okay, so that's what I said. And just to show you to see how counterintuitive these algorithms are. Like, there's nothing here. Like, why do you group the coefficients in this particular way? Like, there's some quite kind of defined some sort of structure behind it. Like, what is the it's hard for humans and therefore for it's not too balance in the first place. So when we were working on AlphaTensor, the first thing is like, okay, how do we formalize the space of algorithms to do the matrices? Like how, so that we can search that space. How do we do that? And with matrix multiplication, there's a neat way to do that. And in fact, if you think of a linear operation, like say like a rotation by 45 degrees or something like that, this is linear operations are fully characterized by a matrix. And this matrix does not depend on the input. So this is the matrix that characterizes the operation of rotating by 45 degrees. For matrix multiplication is a bilinear operation, and bilinear operations are fully represented by a tensor. So this tensor here is called matrix multiplication tensor, are fully characterizing the operation of multiplying matrices, regardless of the particular matrices that we are multiplying. To see where this tensor comes from, let's consider again the example of 2 by 2 matrix multiplication. And essentially you form a tensor, in this case 4 by 4 by 4, just like vectorizing essentially like the inputs of the matrices. So you have 4 entries here, 4 entries here, and 4 entries here. So that's where you get 4 by 4 by 4, like one axis for each matrix. So 2 axes for 2 input matrix, 1 axis for the output matrix. So if you don't have the tensor, it will have some mostly 0 everywhere, but it has a few ones in this tensor. So for example, corresponding to A11 and B11 is linked together. I think it's better on the next slide because they're multiplied together, and the result is written into C11. So the line corresponding to C11, A11, B11 is 1 in the tensor because all these elements are linked together. And similarly, C11 also depends on A12 times B21, so you put a 1 there in that to indicate that this is also linked together. And then if you keep doing that, the number of ones of this tensor is going to be NQ, which in this case is 8, because we know that, but not by coincidence, that actually the number of multiplications of naively multiplying matrices, right? Like if you multiply 8 multiplications, multiply 2 by 2 matrices naively. And okay, so the next point that I want to make is that finding an algorithm is the matrix multiplication is the same as the composing this tensor that is explained. And by the tensor composition, I just mean an expression like U, V, W, like same as the matrix multiplication of tensor. Instead of 2 elements, we have 3. So to see that, I want to say that there is some number of factors in the decomposition, let's call it R. And I want to make the point that this R, this number of factors, will indicate how many multiplications we need to do in the corresponding matrix multiplication algorithm. So let's see that with Strassen again. So this is the same algorithm that I showed at the beginning, Strassen's algorithm. There are 7 multiplications. How do we convert this into the kind of tensor decomposition view? Okay, so this is the tensor we want to decompose. This is the matrix multiplication tensor for 2 by 2. So we form this one of these factors for each multiplication that you require in your algorithm. So for instance, the first multiplication is you take the first element of matrix A and the last element of matrix A. So we can put the information between once at the very beginning and the end. Then you multiply by the first element of matrix C and the last element of matrix C. So same thing, one at the beginning and at the end. And then we store the results in the first and the last element of matrix C. So we do that here. And that's here. And then the next multiplication says, okay, same two elements of A, same two elements of A, only one element of B, only one element of B. There's this one here. And then start the results in these two elements of C. You have to flip the sum of one of them, but they flip the same here, the start results. So that's how you build that's the correspondence between algorithm and tensor decomposition. Of course, you do that for all 7 factors, also entries here. And that's why having 7 multiplications is the same as having a rank 7 factorization of the tensor. Okay, so with that in mind, we already characterized the space of algorithms as the kind of both desired tensor. So we create a single player game because alpha tensor is based on alpha 0. And alpha 0, as you might have heard, is a real agent that learns to play, originally it was the same to learn to play games. So we got the problem of finding a decomposition as a game. So what's the game? Here's the game. You're giving a tensor, and the beginning is the multiplication tensor, later it will be something else. So you're given a tensor, and now you have to make a move, like place a piece on the board or something like that. What's the move? The move is to choose a factor 310, UDW. That's the move. Of course, once you play that piece on the board, that will change the state of the game. And the space change is around one update to the tensor. So it gives you this new tensor. Okay, there's a residual, let's say, after applying this around one update. And then you check whether you're an all zero tensor. If you're all zero tensor, the game ends. If not, just use as send the result back to the beginning and then the game is move and so on. That's very, very simple. So that we got this tensor game. And the game ends at step 3, essentially, if you are at the all zero tensor already. And then by construction, the set of moves that you have played are a valid factorization of the tensor. Because, at the end you reach the zero tensor, it means that after subtracting, say, R factor triplets, then that means you must reach the input tensor you had at the beginning. We export the same export to the game. So how do you do when you play this game? You say you play again, you end at the end with a non-zero tensor. So how did you do? We assign a score of -1 for each step taken. So that means that a game with higher score, it will have fewer steps, which means it corresponds to a lower rank decomposition. Lower rank decomposition. And first, we know from the previous slide that low rank means more efficient. So essentially, scoring higher in this game means that you have better ranking. That's the correspondence. And now we train RL agents, which is alpha tensor, that learns to play this tensor game. That is the main thing. There are few technical points here, like when we apply alpha 0, in general we need a discrete function space, and here you can see that when you choose a factor, it's fine. In general, in these factors, you can put +-1 value, you can also put +-2, +- square root of 2, like anything. But we discretize the space, so we allow the factor entries to take some set of values, which in general will be integers, and have to be integers, but in general will be integers. And this is a more practice in the literature, but also allows us to have a discrete set of hashes, which we need for alpha 0. But also the most important thing is that we only care about exact tensor decompositions. If you have an approximate tensor decomposition, then they might not correspond to a valid decomposition. So only care about exact. And the way in which we can validate exactness to the computer is to get rid of floating point operations and then to do everything on the integer game. So it's kind of convenient for us. Of course, it's a limitation, but it's a technical limitation, but very important. And anyways, so you might have function alpha 0 that goes straight for games. In this case, it's the game of Go, and it made impressive results. It uses this multi-kind of research to kind of explore the next moves that you will play in the game before committing to any particular actions, right? So just run this research, and then this follow like a few steps ahead, but how would the game change, and then after having explored some options, then you commit to an action. So we use the same idea here for a tensor, it's the same exact thing. The main difference with respect to board games is that the action space is much bigger. And by much bigger, I mean orders of magnitude. In the game of blood, you have 300 actions per move. For 2x2 matrix multiplication, which is the simplest one, and this 4x4 for tensor, you have 8. And so that's huge. That's really hard to explore this case. So there are many kind of tricks that we have to add on top of zero to make this. I will not go into the details, just mainly because of time constraints. But as you can imagine, there are many asymmetries. And the previous presentation, we like it's always a good idea, or generally a good idea, to get rid of this right? So in here, like you have things like the ordering of actions, different orders of actions will give you the same factorization, because the tensor position doesn't care of this order the factors are presented. There are many other symmetries that we try to relax somehow, or to kind of incorporate or take care of. If anyone is interested, I'm more than happy to talk about that offline, but for the purposes of the talk, like I will just very briefly highlight some of the components of alpha tensor. First of all, it's a distributed system, meaning that it's running on many machines at the same time. Kind of one of the main components is the learner, is one of the nodes of one machine. It maintains and updates the neural network. And then this neural network is sent to all the other machines, which are the actors, which are running in parallel, and their goal is to play games. That's it. And then the actors take the latest version of the neural network, they play the game, and when they run this multi-level research, they are guided by the neural network. And they, in order to kind of compute, in order to compute a policy, like which move to take next, and also in order to kind of assign how good a particular game state is. In this case, it would be like, okay, like given this tensor, how many really good is the approximate outcomes? How many moves will you be able to finish? And of course, this neural network is not perfect. So that's why we're running CTS. That's why after we're running CTS. So if the neural network were perfect, then we don't need to explore several something. We just fully trust it. But because it's not perfect, especially at the beginning of training, we just run SCTS, guided by the neural network. But the idea is that by running SCTS, then we improve the policy a little bit. We follow a policy that's slightly different to that dictated by the neural network. It's dictated by the multi-level research. So it will be a little bit better than the neural network policy. So this game, after finishing the game, playing with this slightly better policy, then we send the game to the learner. And then essentially this game is a data point. And because we have many actors, we have many data points that we will later use to refine the neural network. And then the updated version will be sent back to there. But to that version, that's essentially the loop that will keep improving things. And okay, so one of the components is that these actors played by the games played by the actors are not the only source of data. Here we found it was very useful, that is unlike AlphaGo, to generate synthetic demonstrations. So all the data points. How do we generate data points? Well, we do it in the most naive way possible. Let's generate factors at random, and then compute the tensors that these factors will give to. And we just add as data points. And at the beginning of training, we found that we give a higher weight to these synthetic demonstrations, because kind of let the agents learn the rules of the game. But toward the end of training, the quality of this synthetic demonstration is quite bad. The quality of this synthetic demonstration is quite bad. But at the end of training, we don't wait the contribution in favor of the player games, which will be better. There are many other things, like for example, reaching a basis here. Another thing that we found was very useful is to not have only, so for example, you could run an alpha tensor experiment, say, on trying to decompose 3 by 3 multiplication tensor, and that is fine. But we found it's better to to play many matrix sizes at once in the same experiment, and because there's some sort of tensor of non-sample sizes. And yeah, that was also kind of surprising finding, but it is quite consistent. We found we actually, yeah, it's the thing that made a difference for us to bring the state of characteristics. Okay, so I think that's what I wanted to say. I think that's the second. Yeah. Okay, so for that's the thing I need to say about answer. Then for I will go next to fast steps and AlphaGo. And the main difference of when we move to AlphaTensor to what I'm explaining next is, I would say, is generality. So AlphaTensor, at the end of the day, is a tensor, very good tensor composition agent, but it is a tensor composition. So you cannot do anything else, at least without changes. We did apply AlphaTensor as an observation in quantum computing as well, and in a completely different context. But it was for optimizing quantum circuits. But even in that case, the problem can have certain correspondence to tensor composition. A particular notion of a particular notion of rank and so on, but still tensor decomposition. So that's good because it helps us find this result. It helps us find result in matrix decomposition in quantum circuit optimization, but still, like the problem needs to be framed in somehow as a tensor decomposition. So what if we have want to discover algorithms inside of the domain, and how would we go about that? And then, of course, like after working on AlphaTensor, as you may know, like the scientific happened and the revolution of LLMs. So we started thinking, is there a way to exploit or leverage large language models for other purposes, which are discovering new algorithms? And then so here's one thing that I'm going to show first the result, kind of motivated this line of work. This is the result we found with FastSearch. So here's the thing. We were exploring this problem called the custom problem, and just a very kind of particular and kind of simplified version is like find this set of 500 vectors in 8-dimensional vectors in C3, so 0, 1, 2. Such that not three of them sum to the L0 vector in model K. And then, so we were exploring to make progress on this kind of custom problem. And one thing is that if you think of effectively exploring, and then I provide you with this solution, which is a valid construction, then probably you cannot see much there. Well, for example, because the font is very small, but also because I mean, it's really hard for us to identify any sort of pattern there or to learn anything from that collection of numbers, right? It's a valid solution, so you can very, very easily verify that it satisfies the constraints, that no three of them sum to the L0 vector. But that's not how we write papers, for example, or how additionally we write it. And if you see a paper like this, it's like, okay, it's missing something. How did you come up with this, right? Here's another view of this thing. This is a function that's called getCapSet, and then returns this list, essentially. And yeah, I mean, that's okay, sure, it's not like a super trivial function. It's not something non trivial happening here. There's some collections of numbers, and I don't know where they come from. There's some like why would we think like what it's for, and most computations are competition, but not straightforward. But if you check related problems in the literature, like I think there was one construction called the linear construction, and it was also it's not that far away from how the result is presented in that paper. So okay, the thing is that this, I think we all agree that this description is a little bit more concise and kind of more, at least for us, it's kind of easier to understand. And we were working with Jordan Ellenberg, a collaborator, and when he saw this thing, and started to discuss this type of results, he actually he was surprised that he was learning something by this solution, but because it's code and you can inspect the code and you can learn something from it. So he put it in his told us, okay, actually this prompts like that language model is more concept to the research than your these objectives. I am learning something. For example, the idea of classifying by number of reflections is novel. And so that kind of motivated us to keep pushing on this direction and see how far we can go with language models. And then yeah, so here's another example. This is how AlphaBond, by the way, this is about constructs and AlphaBond. Like AlphaBond is like the built on top of full search. It's a continuation of the work. It's more powerful. So I will focus mostly on AlphaBond because it's the kind of most updated version. But yeah, the result from the release life was from Passage paper. So here's the visualization of how AlphaBond operates. Essentially, it takes some code, right, and then it starts to iteratively refine it. And maybe at the beginning, the code, think of the code as the code that outputs this collection of vectors. And although this function is in some case, but anyways, like think at the beginning, maybe that it produces a list of vectors that they don't satisfy the constraints. Maybe if you're not actually do up to 0, or maybe they do satisfy the constraint, but it's less than 12. So iteratively, then we ask the language model, can you improve your own code? Because I run the previous function and it's giving me only 200 access, not 500. And so it will keep improving iteratively until there's some number of iterations. It will hopefully give you something that you care about. So this is in the case of AlphaBond, the iterations are so every time we create a language model, it will produce like a diff, like the difference with respect to the current code that you have to apply. So that illustrated here with the parts in green and red. So the language model tells you delete these lines, add these other lines in here. So that it kind of edits an existing code base, and that's how it operates. And there are 3 components of AlphaBond, and of course the LLM is a single part. It is the part that is doing the iteration, and there are also evaluators. And here's the thing: we know that when we operate with LLMs, they tend to hallucinate and produce sometimes garbage, essentially things that are either not correct, or maybe code that doesn't run, or even if it runs, it's not. It's not correct. It's giving you something that is not what you want, right? So whenever the LLM gives us some new code, AlphaBond requires or we provide some way to automatically evaluate it, and that's it's super important in this one. So essentially, this evaluator is in charge of 2 things. One, first, checking that the code runs and is correct, and the second is that assigning like a score to the code. So how well it performs according to some metrics, which can be one metric or multiple metrics. And then the thing is, because we assign us some scores that tell us how well this code, how good this code is, then we can apply an evolutionary algorithm to keep iterating over the best previously proposed ideas. So these are the 3 main pieces of AlphaBond. So this is another visualization of the kind of the same idea. Here we assume we have 2 matrices, one and 2, higher is better. And then you start here, and then the LLM will produce, from every point, we produce different pieces of code, and then you evaluate them automatically. And then you end up with the new point in this metric space. you end up with a new point in this vector space, and then because we're running everything that is evolutionary algorithm, it will tend to select the points with better analysis in the next iteration. So every point here will be a piece of code. And then when we run to the LLM, we show, for example, let's say we choose this piece of code here, we show this to the LLM and say, okay, this is where you are at, this is the best program that we have found so far, please improve upon it. And then it will produce kind of cloud of points around the chosen code. Some will actually decrease the metric, some will increase the metric. But for those that will increase the metric, we kind of repeatedly apply the same process and keep improving. That's how we do this to work. Is there any questions so far? Yeah.
When you say evolutionary algorithm, are you talking about a way to say from iteration to iteration, or are you literally saying an evolutionary algorithm where you have a fitness function and another combination and an iteration?
We have a fitness function, which is the score that the algorithms provide, and then the mutator operation is the LLM itself. So we show the code to the LLM, and then it applies some mutations, which is the diff. And we also have crossover. Sometimes we have more than one individuals, so pieces of code. We show them to the LLM, and then maybe it decides to combine ideas from multiple solutions, or maybe not. Maybe just random. I don't know if that answers your question. Yeah.
Just maybe a follow-up on that. So you're evolving just the code and not the model.
We're evolving just the code. Yes.
So similar then for the alpha tensor, you're evolving. Are you training a model for that just that specific shape, or is the model able to generalize like over different matrix shapes?
That's very good. So in the just in the alpha tensor and the described before, there's no evolution at all. Just learning, as in training neural network, and through reinforcement learning. And then we did this generalized agent that applies on multiple models. Now here, there's no, we don't actually take any training step. We don't train any model. It's just purely a fixed or a set of fixed LLMs that we don't fine tune at all. So we can do any training, they're just pre-trained. And then we repeatedly query them using this evolutionary approach. Now, to the question of whether you could have the equivalent of multiple matrix sizes and yes, definitely. That's something, like for example, if you were using the cat set run from the previous slide, you could think, okay, I showed it as a point in an n-dimensional space, but say that the input to the function is the dimensionality b, and then the LLM produces some code, and the code have to work for any dimension, for any input dimension. And then you can evaluate it, for example, metric 1 could be result in dimension 3, metric 2 could be the result in dimension 8. And then you that will be like your equivalent of training instances. There's no real training as in the initial definition, but that would.
Do you really need like the biggest LLMs that you have, or did you try out like basically running just a bunch of small models, because then you can run probably a bunch of them?
That's a really good question, and we've been back and forth with that. We will not hear it to us. So the thing is that sometimes the code that the LLM provides is scored really high, and it gives you a really good score, like it kind of even improves the state of the art and so on. But if you look at the code, it's something that for example, I would not have built ever. And it's like there's this trade-off between, okay, how much cleverness is involved into this code versus just, if we use a cheaper model that is producing something that runs that is kind of random and that there's no specific very clever ideas there, maybe that's enough. But choose like some other more clever model, or clever as in the more expensive model. So it was not clear to us. And that answered the question. And with fund search, again, it was like, you don't think of fund search as the precursor of AlphaGo. We did not find we did not really find that getting a bigger model improves the result. But with AlphaFold, we found the opposite. Like bigger models actually lead to better results. And in the end of the day, because also bigger models implies more compute, and in the end of the day, you use a pool of LLMs with different sizes. And every time you have a new query, you choose which LLM to run, kind of randomly, and then so that also helps with having diversity of programs, which is very important in innovation. So maybe most of the time you want to get, maybe you want, again, you would like to always query the most, because we said that they reduce us, but you would like to query the most expensive, bigger models, but we don't always do that, and sometimes some of the others. And that also depends on how the evaluators are, because let's say that you can evaluate your program in 1 millisecond, then in that case, the feedback loop is very quick, so maybe you better use many samples from smaller models and less evaluate them quickly. But if your evaluation takes 2 hours, then it might be better to just give priority to the biggest language models and kind of have better quality of samples, let's say, to evaluate.
What does the evaluation actually look like? Like how broad is, like, how good of a metric is this for actual?
Yes, so that's a really good question. I mean, it's a shame that they didn't get one, they didn't include it in the slides. Yeah, good point. Like, for example, here, okay, I don't know if you can say that here, but essentially, this get captured function is taking an integer, and then, which is the variable breaks the dimensionality, and then returns a list of points like this. So the evaluation function, what it does is to run this function, this get captured with, say, target n that you care about, say 8. And it gives you a list of points, and then first of all, check that all the outputs have length 8. Check that the edges are 0, 1, 2. Check that the not represents to the all 0. Or if they do, depends on the human as when you specify the problem, you might accept that they do not are not a value capset, but throw away the ones that are not, that will break the sample using some heuristics. And then the result of after doing all of that would be the number reduction size of the set. And then when you run this into, in this case, one set, it will maximize the score function, so it will maximize the size of the set. That's one example of how it can be carried. I mean, I can use other examples.
At the mutation set, what sort of mutations do you observe? Do you observe small changes, or does it sometimes completely rewrite the code?
Okay, yeah, I guess the question is about concept or both.
This evolutionary algorithm, so like algorithm.
For fun search, one of the differences of the machine code is that functions look like this. Like this one. So this get capset function, and then when we prompt the language model, we say this is get capset v0 version 0. Please write get capset v1 and improve version, and then it will write the entire function. So that's how the mutation looks like. It can copy if it wants. It can copy the same exact solution. Sometimes it will copy with minor differences. But now that was fun stuff. In AlphaFold, the mutations look like this. So at each iteration, you have some code which can be an entire file, not just a function. And then it decides, the language model decides which lines to delete and which lines to add and where. And it can propose, it can be not trivial. For example, you say, I don't know if you can see this one, but the green parts are new lines that have been added under manipulation. So and the red ones are the lines that have been deleted. So for example, in this particular one, that at the beginning, the middle, and at the end, in multiple places of the file. So essentially, it could do anything, adding a single line to adding touching multiple places of the file.
In the case of code generation, is the evaluation done by the LLM the same instance that is used for the code generation as well?
Sorry, can you say that again? Is that information?
Isn't that used for the evaluation for the generated code? Is it the same instance that is used for the generation as well?
Ah, I think that's one key thing here is that unlike other coding agents or other systems, we don't use LLMs at evaluation time. So they're only used at generation time. So kind of multiplications like cross-order prediction, but at evaluation time we don't ask we don't query them at all. We just run some evaluation function that has been predefined by the user, and then yeah, just that essentially.
So is it more efficient than using another LLM to evaluate?
Well, I don't know about the efficiency. I don't know about the efficiency, but the thing is that we want, in this case, in this work, we want something that you can verify. Like essentially, like for example, if we say we have a capset that is largest and previous capset known, we want to be sure that's indeed the case. So we don't want to have any sort of hallucinations, and we want to every new piece of code and every new solution we want to evaluate it exactly, like to be rigorously, like to be sure that whatever the outcome is something that is indeed the case. And we don't, yeah, if you use something on that component, which you will do, then it might happen, depending on the problem, that it actually gives you a score that's not 100% correlated with the real score. You could have some mistakes. That's not to say you should never use LLMs for evaluation. It's just in our work, that's what we did. But like for example, other works like you have heard of data scientists, it's a completely different approach, and they use LLMs for evaluation.
Have you noticed if the generation process collapse at a certain level in the length of the document that, for example, the code can't run anymore and then it's not able to.
You cannot run because it's not of tokens or something like that?
No, more than because I noticed that after a certain length of the program, normally applying new modifications is kind of very difficult for them to create new errors and keep them. Have you noticed that or not really?
To be honest, we have not. There's another question actually. I mean, not that we're going to instance where that was an issue, but yeah, maybe we should say that we after at the very end of the process, if things are going to, I don't know. So I would say one thing is that it doesn't really directly answer the question, but perhaps here is the feeling that it looks like it's always the same program that's queried. Whereas in practice, it's not always the same program. So let's say that you produce a program that is very long, and maybe it will not perform very well according to the evaluation metrics because it has so many things, and that's kind of a thing you care. Like it could have so many pieces that is kind of perhaps too complex to describe the solution to your problem or something like that, and that's not a problem. If that's the case, then it will not be sampled again, or not likely it will not be sampled again to produce a new branch from it. Yeah, so that's not directly answer the question, but it could explain why perhaps if something is too long in such a way, in a bad way, that's not giving you good solutions, then you will not be explored further.
Yeah, can evolve be extended to the situation when the evaluation process is very long, or if the evaluation is very open-ended?
Yes, that's a really good question. And for the moment, I'll be imposed a maximum time for the evaluation function because, let's say the solution from your LLM has limited loop or something. And then, of course, you don't want to be protected against this type of things. So we do impose some maximum time, but again, it's user specified. Now, the question is more about, how long can the evaluation be and how well. So we don't have a very good answer. We have some rule of thumbs. We have found that with evaluations that are up to the order of a couple of hours, then you're gonna see that layer fall off. More than that, it starts getting challenging, but yeah, ideally anything in between minutes, seconds, 2 hours is back, yes.
As I understand, you don't just pick the best
No.
solution each time, you have
No.
like diversity.
There's something, yeah.
How do you define diversity in code?
Yeah, well, we don't directly define diversity, like we have some set up programs, we know there's course, if we evaluate them. And then, for example, one way that you could sample for the next round would be proportional to somehow proportional to the score of the program. And probability proportional to the score of the program. We do something more complicated. In evolutionary algorithms, there are multiple ways in which you can do that. And one way is having islands. It's called like that. And then in each island you have programs inside, and then when you sample a program, you first sample which island to be from, just randomly. And then within that, just pretend that all the programs that have been generated are those in that island. Sample from there, and then go back and then start a new program in that island. And in a way, that's like having multiple experiments running at once, because islands do not really communicate to each other, but from time to time you do some sort of normalization and sort of saying that island, all the programs in one island are performing very bad, then just throw away the way it starts at the island with programs in other islands, for example.
Is the islands based on how the true
No.
solution split? No, it's
Just randomly, yeah. And then that's one way to keep some sort of diversity, but we don't really measure full diversity, or I guess we could do that, but we don't really assign a score like how diversity. But it's very difficult to do that in practice.
Yeah, I also have a question regarding the evaluation of the answers, basically. When, for example, when you train an ML agent, usually you have to spend a lot of time to reward engineering. Was it, for your case, similar? You also had to spend a lot of time like engineering the answers functions?
Yes. You're talking about Algorithmic because it's the element, or
No, I'm talking about other.
for example, requires a lot of engineering because it's a distributed system as well. We have LLMs that are serving. We have evaluators that are running, and we don't have this one evaluator running all the programs. We have multiple of them in multiple machines running programs. And so to make that such a distributed system to work, you do require some engineering work, of course. I would say that so there are two types of, like for example, just to confirm it with RL from the previous platform investigation. RL, there's a lot of work in synchronizing actors with a learner, and also like assigning parameters and how exactly. Yeah, there are a lot of in RL there are lots of parameters that have to be tuned the right way, otherwise it's not. Here we don't have that as much. I mean, that part have also parameters, but it's not as impactful. I would say it's much friendly to work with system. But yeah, that requires engineering in the sense that at the end of the day, it's a distributed system with running machines. They have to communicate to each other, and yeah.
Yeah, maybe got this wrong, but I was talking more about reward engineering, or like engineering business function.
Sorry, I completely misunderstood the question. And yeah, reward engineering as in hacking the reward function, the value function, or something like that. Yeah, here there are multiple ways in which you can define the value function. Like for example, I mentioned before, like you could say, okay, this is the number of this is the size of a set, but you could also say, okay, in this set and this subset, there are three vectors that do satisfy the constraint, that is the sum up to zero. So I would remove them, and then you get the size of the set after removing them, versus just saying, oh, this construction is incorrect. So in that sense, yeah, there is some kind of engineering that you have to do, but I think, yeah, but it's not, that's about it, essentially. There's not much more, something more fancy than that involved. And in most problems, the reward is very natural. It's just, well, the size of the thing, and for matrix multiplication will be the rank for the matrices, like things like that. It's not, it's kind of intuitive. It's not very difficult to come up with this.
Hi, yeah, so I did have a question about the alpha tensor that you were just mentioning, because in a lot of reinforcement learning or mathematics problems, it's like you were saying, the action space is so big that the reward is really sparse. So I was wondering what you guys did to actually get around this sparse reward.
Yeah, but there are a few things, and yeah, I mean, like for example, like one of them is this central basis. Like we don't, otherwise we would always play the same game, like starting with simulation based methods, and that would be not great. So first thing we do is that you take your tensor and write random central basis to it, and then you play the game on that other basis. And then that has also that sort of diversity to the solutions, and then kind of improves the neural network a little bit more. So that's not yet complete. There are also others, like taking into account the permutations of actions. Sometimes you play a game, then we permute two actions, and that's essentially the same game. But and that's the permuted one to the network, to learn from it. Yeah, a few more things like that. Yeah, I know that's. And there's another thing that, like for example, when you produce a factor triplet, let's say that you say the factor triplet is UDW, let's say you multiply two of them by -1, then the rank one tensor is the same. So that's another symmetry of the problem. So what we do is through some sort of normalization, so we normalize its factor of triplets such that the first non-zero entry of the first vector is also, and then that's how we present to the but yeah, some tricks like that.
So with those tricks, do you have like any sort of like quantitative metric to how much the action space reduced, or just?
I mean, technically, the action space doesn't change, as in, yeah, for example, showing the actions in a normalized way to the agent is not a hard constraint, it's a soft constraint. We always present it in this way. And then the neural network could potentially sample an action that does not conform to the normalized version in principle. But like I said, the probability of this will decrease over time. So I cannot really give you a number like how much it reduces because it's in a soft manner. But yeah, yeah. Sorry, that's not.
Thank you.
So I want to talk, this is an implementation of anti-evolve, and I guess what I want to say, because I already described the system, what I want to say from this slide essentially is, this is not an agent that, that's to say, okay, here's the problem, please solve it for me. It requires some interaction, so you have to do something, right? Like as a user, you define, for example, the evaluation function. This is the evaluation function, and you have to write it for them. You don't have to write an initial solution. It's can be very simple and can be very absolutely suboptimal. But you have to write an initial code for the agent to then evolve over it. And like I said, like for example, in the capset, in the capset function, we just return the empty list, and it's or just a vector. And it can be as simple as that. That's something. Yeah. And of course, like in the prompt, you can also include things like something that describes your problem. For example, I'm working on communication with what the composite extensor, and so giving some background. And all of these details, of course, like will matter. That's how to be provided by with the expert to see, right? The practitioner in this case. The alpha evolve, the components I kind of mentioned already. This validated tool, as mentioned, it's many machines running in parallel, either with CPU, GPU, or TPU, depending on the needs of the problem. The program database is where all the programs are stored, and together with the score that has been measured by the evaluator. And then when you sample from this program database to form a new prompt for the element, you sample, as I've explained before, the probabilities that depend on how good the program is. And then this will form the prompt by including some special problems, some previous programs to perform well, and we give it to the element. And as I said earlier, to respond to one of the questions, the element is not just multiple element, but multiple elements of different sizes. So larger elements are more expensive, so there's some trade-off of which ones you very more or less. And yeah, I think I've covered everything here, right? So just to give an example, another example of a problem that we tackled with alpha evolve. Here's the description. This is the smallest regular exon in which you can pack 11 regular exons with unit cell depth. And the state of the solution looks like this. So there are 11 unique hexagons, and the length, the side of the other hexagon is 3.94. And we give the same problem to AlphaGo. This bright code that packs 11 hexagons into a bigger one. And the evaluate function, the only thing that it does is to make sure there's no overlapping in the hexagons, and then measure this the smallest convex hexagon that you can fit around it, and that's the score. And then you want to minimize that. And it came up with a solution that is a little bit better than. So this is just one example. In which AlphaGo found something that improves very little, but still kind of improves the state of the art for that problem. We actually applied AlphaGo on a set of over 50 mathematical problems. Some are coding problems like this, but including analysis, geometry, and combinatorics. In 75% of them, it rediscovered state of the art, which I mean that number by itself I find impressive already, because it's not, there are many non-trivial solutions there, but also 20% of them actually gave something that's better than the state of the art. And one point more about this slide is that the number, and we consider it works, is that like to set up these, to run more than 50 runs, it actually took very little time, human time, as in it's very, very easy to set up this regular problem, like it's evaluate function, it's like running perhaps it takes few hours, essentially, or yeah.
I have a question for the next slide. So, seeing as you rediscover 75% of state of the art, is there a chance that the LLM has seen these state of the arts somewhere?
There is a yeah. We're gonna exclude that option, and I would say, that it's more. I mean, we're gonna exclude the option, but I would say I think that's not the case, because most of the times this is described not as code. In mathematical papers, you don't have like a code that puts the only once you have the construction, then of course you need the box and plug it. But it's not like the process of coming up with the center from the hexagon and the rotation in different places. It's really code in the mathematical papers. So yeah, that would be my answer. But we can never exclude it.
Mathematical similarities amongst the problems that were solved and problems that were not solved when you basically showed this to mathematicians. So no.
You mean similarities as in similarities in the
For example, like I mean, certain field of geometry, things coming from a certain dimension, or things that usually like use certain techniques to construct these objects that when you have to use for state of the art this technique, the machine fails. Has anyone tried to study why it fails, how it fails to reproduce state of the art or not?
I'm really looked into that. So it's like are there any patterns of the problems that we don't get to find the state of the art? I don't think it's if there's any existing answer to that. Like didn't see anything. Yeah. But also, like, we didn't really push any of these problems very hard. Like, it's just applying and see what happens. And yeah. And I guess for any of them, like, I always do the possible possibility that it would be better. But yeah, no, I don't think there's a clear pattern that we say, for this type of problems, I want to. I don't think. Yeah.
We tried Alpha Evolve on the matrix multiplication.
Yes. Thank you. Yes. Yes. And so we applied Alpha to improve matrix multiplication as well. And but the way we did it is very different from Alpha tensor. So instead we said, okay, matrix multiplication is, as I said before, it's tensor decomposition. So you could just take your factors and do gradient descent of them, and maybe minimize some sort of reconstructions. You can better construct the tensor and the target tensor. And then that's what we did. So we wrote a gradient-based algorithm. And actually, people in our team, before we had Alpha Evolve, we were working quite hard on improving something. This brain with adding lots of tricks because if you run brains designed to do that sort of machine, doesn't work. Off the shelf. And in fact, we are not the first ones doing this. I don't know, like many people have tried in the past. And yes, there's some results with it, but it's far from being like a good method, say. But now these people in our team are working very hard and they are quite good results at tensor decomposition and finding relatively good ranks, tensor ranks. But then with AlphaMod, we gave the gradient-based code to AlphaMod and said, please improve it. And it made, well, this is a not so much as usual, but this is some of these that were applied to a file, but just to say, like, for example, it changes things like, oh, I don't want to use Adam, I'm going to use Adam W. Or I don't want this initializer, I want this other initializer. It says, okay, here, the loss function that you have is very simple, I will add all these lines and to copy the loss. And I will also add one bunch of hyperparameters in your experiment. So essentially, it's literally like, I have, in this case, just an experiment. We give it to AlphaMod and please improve it. And it can touch different parts, hyperparameters, it can touch loss function, it can touch initializer, many different parts. And by doing that, we got this table where, again, you have matrix sizes. It's like the table I showed at the beginning, the best known run and the AlphaMod one. And it's kind of surprising that this approach, I mean, I would have never done any before, to be honest. It's kind of surprised that this approach even recovers state of the art for most of the matrix sizes that we try. It fails in these two cases, but in the green ones, we actually outperform, like produce better rank of these tensor sizes. So one particular is interesting is the 48 here. For multiplying 4 by 4 matrices. The state of the art before this work was 49 and reduced to 48. And that's the result that I'm getting the presentation of say 48. Yeah. Okay, so I think I just want to say that one interesting thing about this solution is that the solution comes from using complex numbers. So even if you want to multiply real value matrices, the coefficients that you multiply with are complex value. So all the intermediate operations are complex value, but then at the end there are cancellations and then you recover a real value matrix. So these 48 multiplications are actually 48 complex multiplications, which one could argue, okay, one complex multiplication is more expensive than one real value multiplication. And it's true. The asymptotics are the same. The asymptotic doesn't change. But yeah, that's good. And actually, after we published it, which was what, 2 months ago or something like that, someone took our pattern for 48 and mapped it to something that only takes grand matrices. I think it's, I don't know how it is, but it's very, very cool.
Did you try and run this with some of your smaller models as well? I'm just thinking, will these alpha evolve once you get larger models or better LLMs, right? Like, will it just discover even better algorithms? Have you tried like switching out the LLM?
Switching the LLM for
your alpha evolve?
Yeah, I'm not sure if it's what I said. It's not to try multiple LLMs, but they're all within the DNA family.
Yeah.
If the question is whether you use something outside, like some llama or something like that.
I think my question is to gauge, so right now, some of the algorithms, for example, it went from 98 to 96, right? Like maybe with a new Gemini model that is better at coding, you could get not to 96, but maybe to 95, right? So my question is, have you tried to experiment with some different Gemini LLMs inside of AlphaEvolve to kind of see, okay, Gemini, the big one is really good and got to 96, and the smaller ones only got to 97 or so?
I think, yes. But one of the LLMs have different sizes. The models it hard to attribute the result to one model in particular, because every time you sample a graph, maybe to get this, there are 15 mutations or something. So maybe the first mutation was proposed by the smaller model, the second mutation was proposed by a larger model. It's very hard to attribute it to a single model. With that said, these models are used here kind of quite recent, relatively recent. But yeah, we got results like, I don't know, a few months ago or something like that. So I don't know, maybe if we had newer ones, maybe we could improve this even further. Yeah, to be done, yes, 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 yeah, I don't know how we're doing with time.
We kept like 2 minutes.
Yes. Okay, so yeah, we're almost done. So I guess I'm almost done actually. Yes. Okay, so well, okay. I will skip this as not to say like we also apply these to algorithms that are not scientific or mathematical, like things inside Google, and got some things that are interaction, okay? Because of the time I was skip. This I kind of already went through it, and we just jump to the conclusions. And then, so yeah, algorithmic discovery is a very challenging task, but we have shown a few examples in different domains where AI can be progress and sort of asking capabilities. Of course, the things are still far from fully solved, and perhaps we need more general methods with different capabilities. But we have also seen that one common theme in this talk is that starting with alpha level was highly specialized for test level composition, moving to alpha evolved, which is quite more general, it's not only for test level composition. However, the results from alpha evolved can improve on those from alpha dense, which is kind of surprising, or at least for the more general method can give better results than specialized one, if significantly not. Also, the other thing about this presentation is that programs can be explored in different ways. Like, for example, you can search for the selection of variant, you can use vectors, you can find a function that constructs it from scratch, give you a function that there is vectors, or you can evolve a set algorithm to find it. Give you an algorithm that searches for these vectors. And there's kind of all these three approaches we have seen there in action already. And then there are next steps. I guess that I use this a lot when you have automatic operators, that may be 3D sometimes or expensive. Say, think about the sciences or some other domains, so maybe we need to extend this combine with ideas from scientists, lots of things, and then evaluators instead. Yes, of course, we like to explore more. With that, I conclude. Thank you, everyone.